Then, hello and welcome to today's lecture. This lecture is about data analysis, and in particular we will be looking at one specific data set. This specific data set is, of course, something that we are familiar with. It's growth curves, OD 600 growth curves that you heard about last week. And this is the paper, just to get an idea of what they were doing. In particular, what they were doing, they analyzed different strains of bacteria, and they analyzed them, they exposed them to different chemicals. And in total, there were 168 different chemicals that they exposed their 26 strains of bacteria to. And they also, of course, had a control, like something that should not affect the bacteria too much. And this is this DMSO chemical that they just used to have like a baseline growth curve. And every chemical can either be beneficial or adversarial. And like, of course, most of the time we find out that if you put too many chemicals into a bacteria, they will not live as long. And in particular, they looked at this, and here's just a small screenshot of a part of their data. So here we have strains of bacteria. Here we have some of the chemicals, not all of them. And red is a negative effect on the growth of these bacteria. And we will try to kind of understand their data with our methods. Okay, so this will be kind of code heavy today, because we have to kind of dig into the data, and this is, of course, we do with code. So the first thing that we do here is we download the data set. This is around 300 megabytes big because they're a lot. They're just a CSV file, just rows of data. But of course, like for every combination of strain and chemical, there are multiple readings because they ran their experiments over 72 hours, and every hour they took one specific reading. So this is the first thing that we need to do, kind of download. This we already done. And then we have this data file, this isolate growth curves.csv file, and then we want to look at it. Looking at a CSV file or just like or an Excel file can be done with the pandas library in Python. This is the standard, right? So we imported this here, of course, like the PD, and we're just reading the CSV. And this gives us back like a data frame. And then we could look into just how the data looks like. So for example, here we already did a color mapping, but let's forget that for a second. Even without that, we can just look here at the data, like what is the shape, and so how many rows does it have, and how many columns does it have. And so here we see many rows, some columns, and then we can just display the whole thing. And here, so this we do with the structure here. So again, forgetting about these three prints where we already use the columns that we will set in a second. But here we can just say data.head, and we can display that. And what we see here is just the first 5 rows and all the columns. And here we see, like we have multiple columns, the time, which well it is. Like they did it on a 96 well plate, so they're numbered from A1 through to H12, and kind of what the optical density was when it's measured, and so on and so on. There were replicates for everything. And then we want to get a sense of like how do we get to the combinations of chemicals and bacterial strains. And here we already see something. We see this compound column. So this sounds like a chemical, and indeed it is. So compound is going to be an important row for us. Then we can look here. So here, who's the supplier who supplied the bacterial strain? But here's also another interesting column, which is strain. This sounds something useful. So here it says IL74. And currently we don't know what it is, but let's look a bit further. So here we see a bit more, and here we see a species, for example. This is a bacterial species. Okay. And we know that for every species, there can be like substrains from that. Of course, there's like the whole classification for it, and where it's from, and where it was collected, and so on. And here's just some ID, like some identifier from this. Okay, so once we have this, we can look further. So this is why we already defined here these column names. Like the time is going to be important. The optical density, of course, will be important. Species, strain, compound, rep is a replicate. So the authors have, for the most part, 4 different replicates. So every experiment did it 4 times, which makes sense. Okay. Looking further, so now we can look into the species and strains. So let's first here, let's look into the species. So we can just go into the data frame with the string, which is the species column. In our case, it's just species. And then let's just only look at the unique values here. And here we see that we have 24 unique values. So we have 24 different species, which is a bit different than the 26 strains that we're working with. So maybe for some of the species, we have different strains. So we can look into this here. Let's do the same thing again with the strains now, only the unique ones. Here we see 26, and they all have these different numbers. But here, what we don't know yet is whether like this is a proper data set or like a proper refinement, rather, the strains from the species. So what we would, of course, expect is that like every single strain here corresponds to exactly one species, and that there's not like one strain that belongs to two different species, which wouldn't make any sense. So to check whether that is true, we can again look into the data and look at, and this is kind of a weird syntax, but what it does is like it looks at the different combinations of species and strains. And we drop the duplicates, so on the unique values, or unique pairs, we sort them, and then we see 26, which is a relief. So here we see kind of, if we do all the combinations that occur of species and strains in the data set, we get 26. And even we get the whole list. So here we can find out that this bacterium, this species, has like 2 different strains. And I guess another one here as well. I guess here, this one, also 2 different strains. And every other species only occurs in a unique strain. Okay. So then we look at the compounds. So here we do the same thing. We look into the data frame, unique ones. How many compounds do we get? 170. Our authors claimed 168. So what's going on? Maybe it's not that important. We could go through the whole list. Like, just spoiler alert, they have something that's called empty, and of course the control, which is DMSO. So that makes sense that they have this 168. Okay, and then just to get an idea of like how many times every strain occurs, we can again do for every strain like how many times each value occurs, and this is this value counts method that we call. And then we do another like sanity check, just to get an idea of what we could expect. So what's the theoretical maximum of rows per strain? So we have 170 different configurations of chemicals. So the 168 chemicals, empty and DMSO. In the best case, they do 4 replicates. And in the best case, they have 73 different readings. Why? Because they go over 72 hours. So at time 0, there's 1 reading, and at 72, so it's 73. Just to check whether we get that. So here we see 42,000, 48 for the first few, a bit less for the others. So here it drops down to 27,000. Maybe they had to drop some of the replicates or something. The theoretical maximum is 49,000. So we don't get all the data, but so we have to expect that some of the data that we would expect if it was 4 replicates, 1 reading every hour on the dot for every growth curve, maybe that's not what we can expect. So we might expect some of the data to be dropped. And this is very typical. Like in data sets, most often you find some some incoherences, some things that are not like you would expect. And to get another idea of like how these things look like, we can plot the growth curves. This is just a very small script that does that. Just does the first strain and the first, excuse me, the first 10 compounds here. The first 10 chemicals. And here we have like different growth curves. So some of them here go up, some of them here go down. So here maybe this is one of the inhibitions of, of bacterial growth by this chemical. And maybe this here might be the control. Yeah, the red ones is DMSO. So the red ones are the control that grow much better than the others. Okay, so now we have we know what the data looks like. We looked at it. And now let's think about like how to analyze this data. So what the question that the authors in the paper asked themselves is like, what are the chemicals that can inhibit the bacterial growth? Maybe it should, maybe it shouldn't, but they just wanted to find out whether it does. And they had this very specific metric that we're looking at. And this is a metric that we have not seen yet, but it's something that's widely used in the area, which is what's called the area under the curve. So you get the growth curve, and you're just doing the integral of everything. So every OD reading, you might do the sum of all of them. Here's the integral from like 0 hours to 72 hours. And this has some advantages over other metrics. So for example, you might have a growth curve like this. Let's say something like this. You might think like a measure of fitness might be, for example, the level of the plateau here. So kind of the OD underscore final. Okay. You might also think that maybe you're doing kind of the maximum growth rate here or something, like mu max. All these things are completely valid, but it has been found that AUC is a more robust measurement. Why? Because like you can have something like this, where you compare this growth curve, or maybe let's do it in the same plot. And this growth curve. Maybe they go to the same plateau. Maybe the other one is even a bit higher, but like we clearly see like a difference in fitness here. Like this growth grows much slower, which the AUC of course would tell you. Like this area is smaller than this area. In any case, this AUC metric is what is used a lot for these kinds of screenings, where you say, is growth inhibited or not? So this is kind of the basic thing that we want to look at. And what they quantified is kind of the relative AUC of a chemical, of a strain exposed to a chemical compound with respect to the control exposed to DMSO. Right, so this is some percentage, or maybe not a percentage, but some ratio. Ostensibly, control might be the baseline, and this might be maybe a bit higher, or a bit lower, or much lower. And kind of now we can, with this number, you can say, oh, it's more inhibited if this number is smaller. It's even boosted if the number is bigger, maybe even above 1. Here, maybe, so we can quantify this, but we can also like just qualitatively say, oh, is this inhibited or is it not inhibited? And there are lots of things, like lots of rules that you can think of whether to classify whether you're inhibited or not. A simple one is just to take one threshold and say, if your relative, if your ratio of AUC is smaller than that, then you inhibit it. If it's bigger, then you're not inhibited at least. And let's just pick threshold of 0.5 for now. We're going to look at the data, whether that makes sense in a second. Okay. Of course, we can have other thresholds. So here's a code that just labels the data. Right, so from our data, now we're creating the labels data frame, which just computes these AUCs and says if the relative AUC is below 0.5, in our case, then then we're going to say this is inhibited. So we're going to give the label 1 to it. Just to see whether that makes sense, so here's a code that draws all of this. So here's the distribution of growth inhibition, so relative AUC. And here is like how often it occurs. And we see like most of the time you're around 1.0. You're not inhibited. You might be even boosted a bit, although that might be due to variation. And then we have a small cluster here where we can say, oh, this is definitely inhibited. You're so low, the AUC is so low that something is going on here. And you see here's a very flat space between them. So we can debate where to exactly set the thresholds to, but like somewhere in between these two peaks of this bimodal distribution makes sense. So 0.5 is at least not stupid here. Okay? And then here we see just two random, or I guess the first two growth curves of one non-inhibited and one that's inhibited. And this is maybe a non-inhibited one, goes up nicely, although it falls down afterwards. And here is kind of an inhibited one. It gets off the ground very, very slowly. And here we also see the relative and AUC values. So here's 0.12, and here it's 0.72. Okay. So if we look at this data, also we will find out, or we already see that kind of the data will be very skewed, very imbalanced rather. So we have a lot of cases where nothing happened, like where we're not inhibited, and then some cases where we're clearly inhibited. This is something that we have to take care of during our analysis. But what we can already say, oh, here we have it. With 12,929 samples, that is growth curves, and 481 of them are inhibited, or are considered inhibited by this rule. So that's 3.7%. So most of if we draw like a random growth curve out of our hat, it's going to be most likely non-inhibited. In particular, we will want to classify whether a growth curve is going to be inhibiting, but just looking at the prefix. This is the goal that I would like to set for this lecture. So we have the whole growth curve over 72 hours. There we can classify whether you're inhibited or not by doing over the whole 72 hours, doing the integral. But let's say, oh, you're a bit short on time, and you ask the question, oh, can I look at like just 1/3 of my growth curve, 24 hours? Can I already predict whether we're going to be inhibited or not? And for this classification task, so one strategy that would already work quite well in a specific sense is to always say, oh, you're not inhibited. You're right like 96.3% of the time. And only 3.7% of the time you would be wrong. But of course, you want to get better than that. Yeah, which brings me also to kind of this small discussion on like metrics. Now we are if this is the question that we're asking, whether we can predict whether a given prefix of a growth curve is going to be inhibited or not. This is a classification task. So kind of we get the data, or here from 0 to 24 hours, 0 hours to 24 hours. And based on this, we have like a box, and we're going to construct different versions of this box, which either says 1, which means we are going to be inhibited, or 0, which means not inhibited. Right? And there are a few metrics for this. Let's draw this here. So the first one that we discussed, which is maybe not the best one, is accuracy. Just like, if I give you a random sample, are you correct or not? It's not the best one because we can easily trivially get like this 96.3% just by always saying, oh, you're not going to be inhibited. So this is not the best one. We do have this, whenever you talk about like a binary classification task, you have this confusion matrix. So you can have like a matrix, a 2x2 matrix. And I have to look up which axis I would like to be which axis. So here we can put our predictions. And either we're going to say 1 or 0, and here's going to be the truth. The truth can either be 1 or 0. And then here we can fill in like how many of our data set falls into this intersection of predictions versus truth. And of course, there are different names for each one of these categories. I'm guessing you know them. Like this would be, if you're predicting 1 and in truth it is a 1, and we're calling that a true positive. You said positive and it's true. Again, if in reality you're predicting 1, but in reality it's 0, it's of course a false positive. And here, this would be like a false negative. We would predict 0, but in truth it's a 1. This would be a true negative. Now we have these two notions, which are the precision and the recall. The precision is like if we're saying 1, like how much of the time are we correct? So under the condition that we set 1, how much of these numbers is in the true positive category? So the precision, which is true positive over true positive and false positive. Which is interesting to know, but there are other numbers that are interesting to know. For example, like what's called the recall. Like if we're giving it a 1, like we know from the ground truth that it's a 1, like how much of the time are we saying that it is 1 and not that it's 0? So that's called the recall, which is now TP over TP plus F, plus the false negatives. Okay. And only knowing these two numbers, precision and recall, and like how many samples in total do we have, and how many of the samples are positive, like the 3.7% number, like only by these two we can reconstruct the matrix. So kind of, we of course would like the matrix to look something like this. We have zeros in the false positives and 0 negatives. So we would like to know like how far are we from being that matrix. And looking at precision and recall at the same time, trying to increase them at the same time, translates into being close to this 0, 0 matrix here. Now, there are two other metrics that we are going to look at, that people also like to look at. So here we have, of course, two different ones. It's precision and recall. There's two numbers that we would like to optimize at the same time. Optimization often wants to be done, or can be done currently, for a single value. And the F1 score is one of these. The F1 score is just a mean of precision and recall. So it's the harmonic mean, but it's not that important. But like it's something between precision and recall. It's well defined. It's not the arithmetic mean, but it's the harmonic mean. So if we want to increase, if we're increasing F1, that we're increasing, let's put it a different way. If we're increasing precision and recall at the same time, then we're increasing F1. And then there's a last metric that is often used, which is called, again, AUC, which is not the exact same thing that we already looked at for fitness. But which looks at a different kind of curve. The curve that people look at here is exactly the precision versus recall curve. So why is precision and recall, why is it a curve? It's not, right? Precision and recall were just numbers. They were between 0 and 1. So what's happening here? So what we're doing here is we're changing the threshold. So we will be looking at models that are not going to output exactly 0 and 1. They might, but they can also output something between 0 and 1. Like the predictions will be in 0 and 1. 0 and 1. This is what the model will give. And then we're going to have a rule that says, oh, there's some threshold that if our value that we're outputting is below the threshold, then we're saying it's 0, it's a negative one. We're not inhibited. And if it's above the threshold, then we're saying we're inhibited. This restricts the class of models, but all of our models will be of that form. And then we can play around with the threshold. We can put it all the way to 0, which is to say we're always going to say 1. We're always going to say we're inhibited, which, of course, then if we're always saying we're inhibited, then our precision is very good. No, our recall will be very good. Right? So whenever we're presented with something that's really inhibited, then because we're always saying it's inhibited, because we have the threshold 0, then our recall will be perfect. On the other extreme, if we're putting our threshold all the way to 1, then we're always saying it's not inhibited. In particular, like our precision will be pristine. We're never saying 1, so we never have like a wrong signal that we're sending. And in between, there is a more or less continuous curve between recall and drawing this recall and precision plane, and the AUC is this area here. Just as an idea why that makes sense, why that at least makes some sense, is like if we're predicting 100% the correct thing, so we're either saying 0 or we're saying 1, then the thresholds almost don't matter because we're not saying anything between 0 and 1, except at the extremes. So our precision and our recall will be perfect, 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 except here when we're hitting 1, then we break down, but just for kind of pathological reasons. So kind of our best AUC, actually it was called the RP AUC, there are other ones, but it's the recall precision AUC. The best one would be 1, of course. Have this whole square. Of course, it's always non-negative. Okay. So these are the metrics that we're going to look at. And now let's get into the methods, kind of the models that we're going to look at. So again, like in the code, you see kind of this function that says extract early data. You can configure that, like how many hours you want to throw away. Of course, I already did that for you. So we have, again, the same data set. Now we have 25 features. We had to throw some of them away because they were actually not long enough. And then we're going to have 4 different classifications, all of them neural networks. And first of all, like whenever we train like a neural network, we're going to do a split of our data set. But yes. But it's unclear. So what we would like is we would like recall and precision, both of them to be big. Yeah. But at some point there will be a trade-off. Yes, but this is also not the whole story, right? So you might have something. Yeah, it's not the whole story because you can have a trade-off. Like some might be big, even though you can increase both of them. Oh, sorry. No, you couldn't increase both of them, but you can have the same sum, but clearly better and worse precision and recall values. Like for example, 1 and 0 would be something very weird. 50-50 would be better. Okay, yeah, no, it generally has this. So here, for example, here we're not concave, okay. And because actually we have like steps. If you zoom in, because we have a finite amount of data. You will have steps, so you can't be 100% concave. Like generally you're concave, like if you zoom out you're concave, but you have this chinks here. Yeah, very good question, thanks. Yeah, again, now we are at like test, validate, train, test, and validate split. So we're taking the whole data set and splitting it up 60% with using to train. 20% for validation, 20% test. Maybe let's forget for the moment the test. Let's say we have some training data and some validation data. Test will come at the very, very end. So what we're going to do is like we give our model to train it, this training data, and then to assess the quality, we're going to evaluate the model on the validation data. Yeah, here we're doing a few things. So this is kind of just standard practice to do that. We're also going to normalize our features. Also random practice to have something between 0 and 1. Okay. We're going to do 4 approaches. The first one is just a naive neural network. So let's try to think kind of what kind of data we have and how that it would make sense to feed that into a neural network. Of course, I'm assuming that everybody's familiar with kind of how a neural network looks like, at least, or what it can do, what the inputs are. So our inputs, in our specific case, are prefixes of growth curves. So we might have something like at 0 hours, we have some reading. At 1 hour, we have a reading. And so on, up until 24 hours. These are OD readings. These are scalar readings. So all this is in R25. We have 25 scalars, which is 1 data point for us. 25 numbers. Okay. So our network would have to have 25 inputs here as well. Let's just put a neural network here. And at the output, we want only one value, which is the thing that we're going to compare against the threshold to say whether we're 0 or 1. And here, this value can be between 0 and 1, or it can be between minus infinity and plus infinity. You can translate between these two by the sigmoid function. But again, like this value, the semantics of this should be that if it's high, then we're confident, or the neural network is confident, that inhibition happens. And if it's low, then the neural network is confident that inhibition doesn't happen. Okay? And kind of here we can, of course, get as crazy as we want here in the neural network. Here we just have like two layers, just with a standard activation function. ReLU doesn't really matter, or maybe it does, but here we just picked one of them. And the thing that we're doing that is because of the imbalance between inhibition and non-inhibition, because we have only a 3% of the data that is inhibited, we're going to add this positive weight correction here in the loss function. So for the positive ones, we're putting like a positive weight, which is the number of negatives over the positives, which is big here in our case. It's like 96% over 4%. And so we are kind of penalizing more if you get like an inhibition wrong. Otherwise, we would always just say, oh, you're not inhibited, and the loss would tell you, oh, you're so good, you're ready to go. Of course, like the square root is like more art than science. You can use something else. A linear tends to be a bit too harsh, but you can use the third root or another function here. Okay. And yeah, so here this is kind of in PyTorch, the implementation of our naive neural network, just 2 layers, input dimension to 8, like this one hidden layer of just 8. Can be anything, guys, but that's what we used here. And here we're using ReLU as the activation function. Okay. Yeah, and then we're training. So here is the training loop. Just we have the standard optimizer that is the Adam optimizer that kind of is the standard, I would say, nowadays. And we have our loss function with this weird square root and negative over n log correction. We put it all here. And here we're just doing like, we're evaluating, we're doing the backward step, and we're doing the step with the optimizer. And that's it. And then we're kind of putting the loss, because we want to have like a plot at the end, into a list. Okay? And here we're doing 10,000 epochs. And this is kind of quick. So here, this I can run for you. Kind of you see that you get, in a reasonable amount of time, you get the output. And we have here we have the loss curve. So x-axis is the number of epochs, like when we didn't start, and the y-axis is a training loss. So high loss is bad, a small loss is good. So we start with some value, and we see kind of it learns a lot very quickly. Then here at some point, and this is a very typical curve, kind of it gets better, but slower and slower and slower, and then we see that somewhere here around 0.1 loss, we hit an asymptote maybe. Maybe with another 3 days of training, we would get even lower, but at some point we stop training here. Okay, so how good is this? That good if we can understand it. So we get through all of our metrics, and we will compare to the other methods when we encounter them. Accuracy, 96.5%. Okay, we would have, it's close to the naive solution, which got 96.3, I think. Okay, but of course, it's not the naive one, because we have precision and recall which are meaningful. Precision just 52%, which is not great. Recall is a bit better. F1 scores, and here at this point we're not exactly sure what to expect because we haven't looked at other methods here. But just to set a baseline here. So the F1 score is of course between precision and recall. It's a mean bit of them, so somewhere in between, and the AUC is like 0.759. Okay, let's keep the numbers in the back of our mind, and let's go on. So the naive approach was just, yeah.
Sorry, that's the AUC of which curve?
The RP curve.
Okay.
This one.
But why do they give a single position of recall and precision then?
Yes. Yeah. Here we set the threshold to 0.5. Okay. In the very last step, we will optimize the threshold. But you're completely right. So the AUC is independent of threshold because it looks at all the thresholds. But here we just set it to something, 0.5, just to have something. But it's a very good question because we will optimize that in the end. Okay. Yeah. So here we just gave all the data, the 25 dimensions, to some neural network. Maybe it wasn't deep enough, maybe it wasn't wide enough, whatever. But we got something out of it. And now in the next two methods, actually, we look at ways to extract some more interesting or ostensibly interesting features out of our datum. Our datum is just this time series, and maybe there's some hidden structure in between in these things. And in the first approach, we would just look at this like very mathematically. And this is what's PCA, principal component analysis, which just tells you in which direction of the data you see the highest variance. We're getting some of what's called the principal components. We can look at like how many we should look at. So here's just some plot or some numbers here based on the first 3 eigenvalues and corresponding eigenvectors. So if you sum the variance of them all up, we get 96.9 of the total variance, and even the first one gets you 81.2% there. And the second one is 11.8, and then the third one, it drops off at some point. Okay. Which means that kind of you could look at you could extract out of your data just 3 different components or 3 different features and get 97% of the variance, which sounds promising. And many people do that. PCA is like a really like a widely used thing. And if we do that, we just put this into like a logistic regression, which is just a very simple neural network. We get this here. So this is not like a 2-layer, just a 1-layer neural network here. We get accuracy dropped a bit. Precision is kind of weird. Recall is kind of high. F1 score, that was a bit worse than we saw in the naive one even. And AUC was even worse. It's also worse than the first one. Which means, okay, PCA, we tried to get to extract some of the important features out of it. It was promising because we saw like the first one got you 80% of the way of the variance, but this variance didn't translate well into actually good performance of our classifier. Approach 3, and I'm going to speed up a bit. We're again going to extract features out of our 25-dimensional vectors. But now we're doing it by hand. Yes? You can look at the eigenvector. Yes, you can do that. It's kind of useful. So I didn't plot it here, but if you look at the first one, you see that kind of it's a growth curve. So it's 25 dimensional, and it looks like a growth curve. It goes up, which makes sense. Like this is the the biggest variance. Like if you take that away, then you're going to have an inhibition. A variance is for the whole data set, right? But you're saying like, okay, yeah. You're extracting the, yeah, okay, this is, you're getting the 25%, the 25-dimensional thing, you're mapping that onto, let's say, 3 dimensions. And now these thing you put into a neural network. And here it's a very simple one, it's just one layer. Like what's called logistic regression, just very simple. Okay, and now we're not relying just on math and variance, but we are going to handpick some features. Something that we think has some biological meaning. We're going to do 5 of them. First one is area under the curve for the first 24 hours, which is kind of makes sense because we want to predict the same thing for the integral to 72. Yeah. Yes, so we're not talking about like computational efficiency here. We're talking about like predicting power. So how good is it at predicting things? Yes, so the idea here would be that maybe the neural network is not able to identify these features. Because it doesn't have, yeah. We see that here in particular when we look at the hand-picked features, that these features are features that the neural network would have a very hard time picking out or learning. But of course, you're right, we're losing dimension. So in some sense, we should lose information, but if you're picking the right features, you can also help the training of the neural network. So in the first case, and then for the naive network, we did have a hidden layer. This was not just, yeah, if we did make like maybe 20,000 layers, maybe it could have figured out something out. It's very possible. Yeah. In this case, most likely, like the learning would have not have converged, but yeah. Yeah, something. There might be a sweet spot. We have not explored that here. Yeah. Okay, so some biological features that we're just throwing out there, and again, throwing that into a logistic regression, so a neural network, area under the curve of 24 hours, maximum growth rate, 24 hours, a recent slope, kind of before the end, the current OD, so the one at the end, has growth started. So just some threshold, like here we started, at the baseline we started, are we at least 0.1 more OD than we started at the end? Yeah. And these things we can extract. We can also plot them. So the red ones, so for all 5 of them, how they occur in inhibited and non-inhibited populations. And then we're just throwing this into a neural network. So again, a logistic regression. And now this is what we get. We get like accuracy around 90%. Precision, I think, was a bit higher than before. Recall comparable to what we had in the second case. F1 scores a bit better, AUC a bit better. Kind of comparable, but quite a bit better. And then the last model that we're going to look at is a convolutional neural network. This is a very specific type of network where it looks kind of at some locality. It looks at local information and tries to aggregate that. So here for a time series, it would look something like this. Let's say here we have, I don't know, like OD0, OD1, OD2, and so on, OD3. And what the CNN does, the convolutional neural network, is to have some window with some specific weights that are common to all the windows, like wherever they are. This would be the same windows here. And to extract some feature here. Extract a feature here. Extract this feature here based on the same, like, 3-input neural network or subnetwork. And now we have different features. And these features we can combine, and we combine them in like a feed-forward, a fully connected network, and then we get one output at the end. There's some pooling going on here between these. Well, the important thing here is that kind of the fact that we're learning the coefficients, like the common coefficients, they're always the same for all of these windows here, means that kind of we're trying to get the network to learn some local features. So here, for example, this could be something like, oh, here we could look at whether we're going up 2 times or something, or whether we're going up and then down. This could be another feature that can be learned. And also the magnitudes of these things can be learned, of course. Yeah, if we're setting this up, this is of course a bit more involved than the naive neural network, but everything here like remains standard, quote unquote. So like we can just instantiate a convolutional 1D network here with 16 channels, let's say, so 16 different features, and then you pool them together, and you just have these linear layers afterwards. A bit more complicated, but it's in the libraries. You can find code for that. This takes much longer to train. Like I think this trained about like 5 minutes, not extremely long, but like still. And here we see something like this. It's a bit more noisy as well because like we made mini batches out of this, but again, like the general trend is the same. Like you start somewhere, and then you're going down, and you're hitting an asymptote at some point. So this is the loss plot again. So here are the epochs, and here's the training class. Okay. Let's look at accuracy and all the rest. So accuracy, again, is like fine. It's very good, like 97%, whatever. Precision was better than the others. Recall, also better. F1 score, better. AUC, better. So here it seems like the CNN won out of all of them. So kind of the naive neural network was fine. PCA was kind of a bit worse. The hand-picked features were a bit better, but comparable to the neural network, naive neural network. And CNN won here. And now kind of looking at these 4 different models, now we also developed some intuition or like some expectation what to look for here. Now we have some, at least for this data set, we have some idea what the numbers, what's a better number and what's a worse number. The second to last thing that I would like to do is to do threshold optimization. All 4 of these methods are neural networks. So in particular, they give out not 0 and 1, but they give you like a continuous value. So we can choose the threshold. Threshold here is between 0 and 1. And here we're just having a very simple like optimization script. We're just saying, oh, please put for each one of them their own threshold and find the optimum threshold that gives us here, in this case, the best F1 score, of course, you can look at other things. AUC would be also fine. Sorry, AUC would not be fine because it's independent of the threshold, but F1 is totally fine here. We're optimizing them, and we're optimizing them now not in the training data. Kind of we already did that because we learned the coefficients with the training data, but we're optimizing the threshold on the validation data. Question, does this seem like cheating to anybody? Kind of we compared, like we evaluated all of our models on the validation data, but now we're optimizing the threshold on the validation data. It feels like cheating, but it's not. Yeah. 20. All these numbers. Yes, 100%. Yeah, exactly. And then we left 20%. And this is, of course, where kind of the answer lies. The test data we never looked at. Set it aside for a rainy day. And now is this rainy day. Right? So because now, kind of course, like things go up, as you would expect. Like now we could be like overtraining for the validation data, right? So we're picking a different threshold for all of them. You see, oh, 20% improvement, 81% improvement, so good. But here, these things are on the validation data itself. Now the retest is on the test data. And here it's just some code that evaluates all 4 models on the test data. And let's see what we find. So these are with optimized thresholds. AUC, of course, is independent of the thresholds. So it's whatever it is. Features was kind of the best one, but the others were a bit behind. But like CNN was close. Like we have, yeah, let's say we have 2 different groups. We have features in CNN and naive PCA. Okay. And now we have like F1, which is like the next most important thing to look at here is kind of here we have 2 groups. In the naive PCA group, we see that the naive NN actually outperformed PCA. Has a better F1 score. So the PCA was kind of nice, was promising with all this nice math and variance, but in the end, in this case, it didn't work out. Then we have features CNN, and here it's very, very close. Like F1 score is the same. So here we could give like a small edge to the features, like the hand-picked features, just because it has a higher AUC. Of course, you can also look at the precisions here. And here you see that, precision and recall, sorry. You see that the recall here is almost the same, but then the precision is a bit better. So our winner, I would say, after the threshold optimization is clearly the hand-picked features. CNN is a close second, then naive, and then PCA. For our data. If you pick another data set, things could be different. Which is why data analysis is like a tough job. You have to do a lot of work because you have to look into all these different directions. Here you put 4, which is not even like, you could have gone much further. As you said, for example, PCA or naive NNN, FNN, we could have gone like more layers. We could have like hyperparameter optimized this. In PCA, we could have picked different PCA features, but then also once we picked them, we could have put it into different neural networks. Features, CNN, of course. And then like neural networks is also not the only machine learning technique to do classification. Right? So kind of it's this whole big field, and it's very hard to find your way around here, which is why you have to pick something at some point. And compare things, like compare models to the others. Here, for example, we picked 4 of them, all of the neural networks in this case, but we could have gone a different route. But it was important that we did fair comparisons for all of them. And we did, for example, the threshold optimization. We did for all of them, and we set different thresholds for all of them. And we did it on the validation set. And then we did the evaluation on the test set. Yes, it's the threshold, yeah. Okay, this concludes our session on, at least the lecture part of data analysis. We have some problems for you, which kind of is looking at this data set in more detail. Like one of the questions is like 24 hours, can you reduce that? Of course, there are other questions. Next week, we're going to look at parameter estimation, which is also an AI technique to kind of get the parameters out of growth curves. We have the CRN model. So here we actually didn't use them a lot, except to guide us to the biological, to the hand-picked features. We had things like growth rate, which is something that occurs in the CRN. But next week, we're going to look at like, once you have like a kinetic model, but you don't know the parameters, you don't know the rates, like how to get that from a data set automatically, if possible. Okay, if there are no questions, I say thank you, and we can, I guess, move on to the problem session. And if you have any questions, just tell us.